Here we're waiting for our first speaker, Julia Brodsky, and in the meantime, I can make you an intro to her. So Julia is an astrophysicist by training, and she's from the Blue Marble Science Institute, so she's a researcher, as well as the founder of the Art of Inquiry School. And this is based in Seattle, USA, so she's from the East Coast, as they say it in the US, the same as Ulysse, who is today with us. And both speakers were so kind to join us and give us an introduction about what the astrobiology is about. So this is actually one of the topics that people don't hear very often. And we're very happy to have scientists to explain this to us and also ask questions. So you can use the chats to ask questions. This goes both for the teachers who protect the anonymity of their students, as well as for the classrooms. But of course, remember that for the class students, you can also join the Zoom with the attendee link that your teacher gave to you. However, you have to choose an acronym, you have to choose a nickname to protect your identity. This is very important for us. So you have to use a number for your school and choose a nickname. I see here that we don't have votes yet, so I will end this poll, maybe open it later. And perfect, Julia, the floor is yours. So thank you for joining.
Welcome, everyone. My name is Julia Brodsky. I'm a research scientist at Blue Marble Space Institute of Science, and I'm also a founder of Art of Inquiry online science program for kids 10 to 13 years old. And today I'm going to talk to you about astrobiology, and especially astrobiology of the icy worlds. So what is astrobiology? If you take a look at the word, you will see that it consists of two parts. One part you recognize easily, right? Biology. Biology is the study of life. But what is astro? Astro is something that you recognize from the words like astronomy, astronaut, and so on. Something that has to do with stars or space, right? So astrobiology is the study of life in space. But tell me, and feel free to answer in chat, is there any life in space? What do you think? I'll give you a minute. So in fact, there is, right? We do have astronauts in space right now. We also do have plants and animals on the space station. We are also planning about building planetary bases.
Bye.
We are planning to take a look for life in the solar system, such as Mars and Venus. We are looking for life prerequisites. What is required for life to start, right? How did the life start? What was the origin of life? Astrobiology also wants to study the evolution of early life. How did it change? How does it depend on the planetary conditions? And how does the life itself change the planet? Because it does. It's not only the planet that changes the life, it's also the life that changes the planet back. For example, plants produce oxygen, right? And it changes the atmospheric composition of the planet. We are looking for potentially habitable exoplanets, the planets outside of the solar system. We are thinking about the future life in space. Some people are searching for extraterrestrial intelligence and even sending messages. And some people are thinking, how could we communicate with a non-human mind? So as you see, astrobiology is a very interesting science and very interconnected with all other sciences. So let me ask you this. Do you recognize this planet? There is something strange about this planet, don't you think so? It looks, similar to Earth, but it has no land. There are some rocks forming on the sea floor. There are some first microorganisms emerging in the ocean, but that ocean is very different. The composition of that ocean is very different from what we have now. What is that planet? And that planet is our early Earth, billions and billions years ago. So the early life emerged in water and stayed in water for a really long time. So does it mean that water is a prerequisite for life? Does it mean that we should search for water in other worlds? What do you think? Again, please share your thoughts. I'll give you a minute. So people say yes, right? So if you think we need to look for life in other worlds, what do we know about, look for water in other worlds. What do we know about water in the universe? What do you think? Is there a little water in the universe or a lot? And in what form it is? Is it mostly liquid or is it mostly solid? Or is it mostly vapor? Can we find any water inside the stars? Can we find any water around the stars? Do you expect to find water on the planetary surface? Or do you expect to find the water inside the planets? In the interstellar space as gas, or in the interstellar space as ice? What do you think? So again, take a minute and share your thoughts. I do see your answers here. So first of all, a little or a lot of water in the universe? So looking for water in every form. To tell you the truth, we don't expect to find any water inside the stars, right? That was just a tricky question. But other than that, yes, we do find water around the stars, on the planetary surface, underground, and in the interstellar space, both as ice and gas. In fact, the largest and oldest mass of water that we've discovered is 140 trillion times the amount of water in the Earth's oceans. Trillion is a million of a million. Huge cloud of water vapor surrounding a quasar. And it's easy to understand why it is so. Water is H2O, right? It's hydrogen and oxygen. Hydrogen is the most abundant element in the universe. Oxygen is the 8th abundant element in the universe. So it's not that difficult to put those together and make a lot of water. So, but what if we look for water in the solar system? Where do you expect to find water in the solar system? What are some of your suggestions? It's very difficult to hear you, unfortunately, lots of noise. So if you could type in chat instead, I would appreciate it. Planets and moons, Mars, yes. Actually, there is some water on Mercury, even though it's so close to the sun. And not much water on Venus. Most of the water on Venus boiled out and flew away. On the moon, yes, we know there is some water on the moon under the surface. Mars has icy poles, right? The asteroid belt has asteroids that are icy asteroids, just piece of ice, right? And Ceres, the biggest asteroid in the dwarf planet, more in the asteroid belt, has probably an under ice ocean. So the icy moons. How many moons are there? Lots of moons, yes. But why should we care about those moons? I skipped. Sorry. I wanted to show you some of the moons here. Let me share the screen with you. So our Earth has just one moon. Mars has 2 moons. Now look at Jupiter. Isn't it beautiful? Now look at Saturn. Uranus and Neptune. So many of those moons are icy moons that have lots and lots of ice. But what about water? Right? Isn't it too cold for life on those icy moons? They are far away from the sun. Aren't they all solid ice? What do you think? Should we even look there? Life? What is your guess? And again, feel free to answer in chat. I see your answers. So lots of people may actually worry about that. But in fact, it's not that bad. So let's take a look on one of the moons of Jupiter, Europa. It's close to our moon in size, just so you imagine yourself it a little bit. And potentially it has a salty ocean under a thick crust of ice. So NASA plans a robotic mission to Europa to drill through the ice and send a floating robot into that ocean. And of course, we should be very careful. We don't want to bring our microbes. We want to avoid the contamination of those icy oceans. But how could it be? How could it have a liquid ocean? Here is the answer. Ice is less dense than water. So ice is floating on top of the liquid water, protecting the ocean below from the cosmic cold. And inside, the planetary or the moon cores may be hot. On this picture, you see some volcanoes, you see some hot springs called hydrothermal vents that heat up the ocean a little bit. So, but what happens? What heats it up? Why do they have all of that activity? Here, and what I want to show you a little video that talks about what happens with Europa and how Jupiter actually helps to heat it up. So let's watch.
It was 405 years ago that Galileo Galilei discovered the moons of Jupiter and revolutionized our understanding of science at the time. No longer were we, the Earth, the center of the universe. Europa might have a similar prospect. Europa is among this family of Galilean moons, Io, Europa, Ganymede, and Callisto. It's a challenge to explore Europa because it's immersed in Jupiter's giant radiation belts. Jupiter's magnetic field is enormous, acts to accelerate particles in the Jupiter system, and therefore makes it a challenge to explore Europa. When you look at Europa, it doesn't look like our moon or most other natural satellites. It's not covered with craters. And from the sparsity of craters, we can say that the surface age of Europa is about 60 million years. So something has repaved Europa's surface in the time since dinosaurs roamed the Earth. This is what we think the interior of Europa is like. A thin skin, about 100 kilometers or so thick, of H2O. It was a magnetometer that told us there's probably an induced magnetic field at Europa. And what could be causing that induced field but a salty liquid water ocean relatively close to its surface. As Europa and Io and Enceladus go around their parent planets, it's in an eccentric orbit. So as they get closer to the parent planet, they're stretched out, and farther away they contract a bit. And Europa's orbiting in 3.5 Earth days. Every 85 hours, its surface is going up and down by about 30 meters. So that flexing is causing heating, frictional heating inside the moon, which can maintain an ocean. It can also cause cracking of the surface. It's a bizarre array of ridges and bands and cracks that we think are related to this flexing and kneading of Europa's surface. That ocean, we believe, is in direct contact with the rocky mantle below, making it pretty unique among icy satellites. One thing we're really trying to get at in understanding the potential habitability of this probable ocean, first we want to confirm the ocean, we want to understand, is there communication between the surface and the interior? Because on the surface, we know there are lots of oxidants made by the irradiation of Europa's surface. And if those oxidants can get into the ocean, that would be a fantastic fuel for life.
Okay, so I guess you got the first taste of what's going on with those moons, how they go around the Jupiter and change their shape, how it all heats up the moon. So, but that was the moon of Jupiter. I also wanted to tell you a little bit about the moons of Saturn. There are also icy moons, many of them, and some of them also have under ice oceans. So how many of you have heard of the moons of Saturn?
Could you repeat the question, Julia, so we can put it on the poll as well?
Sure. How many of you have heard of the moons of Saturn and which ones you like the most?
Okay, it's a preference question as well. Thank you.
I can do that. Right? So the Saturn is famous, about its rings, but what about its moons? Interestingly enough, NASA is going to look for Titan, yes. Titan is actually an amazing moon, and NASA is going to send a mission there as well pretty soon to search for life. But Titan is not an icy moon, and Enceladus is another icy moon that we're going to talk about today. So Enceladus is a very small moon, but a very interesting one. The Cassini probe was flying to explore the Saturn when it saw strange, really high geysers going out of Enceladus, going about 240 kilometers high. It's like approximately the distance between Paris and Brussels. Just imagine a geyser that high. It's so high that it actually snows on the nearby moons and asteroids. Just imagine another moon going on top of you and it snows from there. Quite an amazing thing. So it looks like Enceladus ocean has the same salinity as our ocean. And all these geysers provide lots and lots of fine snow that if astronauts go there, that would be perfect for skiing. So I have another video about Enceladus. The problem with the video stopping was because I clicked on my slides by mistake. If the previous one worked fine, I can turn on this one.
I think it worked fine if we close the cameras, we help with bandwidth.
Okay.
And keep in mind how much minutes you would like for questions, given the time slot.
Yes.
Okay, thank
you. This was the last video. Oh, before, sorry, forgot about this one. So what would be the source of energy for all that life on Enceladus? So here on Earth, we have what is called hydrothermal vents. These are essentially hot springs powered by undersea volcanoes. And those hot springs provide all the nutrients necessary for life. For example, it supports like gigantic tube worms that can grow up to 2 meters long, and different types of crabs and bacteria and so on. Those living organisms don't use the photosynthesis. They live below the surface of water. They live very, very deep. But they use chemosynthesis. They use these chemicals produced by the hydrothermal vents to support their life. So let's watch now. And we're not going to watch the whole thing, so I'll
follow the water. Could these mysterious plumes be made of water? And could this water harbor alien biology?
Where there's liquid water, that's one of the key steps to finding potential life.
The scientists are looking for 3 key conditions that led to life on Earth. Liquid water, a high salt content, and evidence of a hot active core deep beneath the sea. After 3 years of intense reprogramming, the probe is finally ready to skim the surface of Saturn's 6th largest moon. NASA's billion-dollar probe could finally answer the question of whether there is life beyond Earth, if it survives the close encounter with Enceladus. At 32,000 miles per hour, NASA's Cassini probe dives through the geysers of Enceladus in search for life-giving water. One of 22 sorties over the frozen world.
When Cassini flew through the plumes that are shooting out of Enceladus, it actually had a chance to taste these plumes, to smell them, to see what they're made out of.
After an agonizing wait, the data confirms that the geysers erupting from the icy moon are liquid water.
The discovery of these icy water vapor jets on Enceladus is probably the most important discovery of the entire Cassini mission.
But water is only the first ingredient for life. The other essential components are salt and heat.
Going deeper into the plume, the spacecraft collected particles and showed that they had salted. That's a big deal.
Scientists believe salt interacting with chemicals from underwater volcanoes could be how all life begins.
There's chemistry that happens when water, especially salty water, is in contact with a rocky surface. The water inside Enceladus that's being sprayed out into space has a salinity that matches Earth's oceans. That's huge.
Further readings reveal the oceans on Enceladus are astonishingly similar to our own.
There were elements in the plume that clearly showed that the water in the ocean was hydrothermal.
Something within Enceladus is heating the water. Heat is the final missing ingredient in the quest for life, the catalyst for the chain reaction that kick-started life on Earth.
It's got everything we were hoping to find. It's got evidence of liquid water, organics, nitrogen, energy source. It was unbelievable. It's not.
So, as you see, astrobiology is not such a strange science anymore, right? So we're different space agencies are planning to send missions to the icy moons pretty soon. There is so much unknown in the universe that is open for you to explore and to discover. So with that, I guess we have to end this little session, and please ask me your questions.
Thank you, Julia. That was a lot of media that we saw there. I mean, a lot of imaginary trips to the moons because we are still preparing for them, right?
Yes,
so,
yes. No, the Cassini mission actually.
Yeah, sorry, the Cassini has happened. Sure. The video. I mean,
the Europa mission. The Europa mission is being planned. Yes.
Yes. We are actually now open for questions. So we can receive your questions either here, either on the YouTube channel. And in the meantime, I can maybe ask a question to Julia until the first questions come in. But we're gonna wait for a few seconds. Anastasia is also gathering the questions from the YouTube channel. And may I ask something? You mentioned something about heat, right? because of the stretching of the moon around. This happens in both moons, like both on Enceladus and on Europa?
Yes, both the Enceladus and Europa are being heated by their massive counterparts, that they're orbiting right now. Europa is being heated by Jupiter, and Enceladus is being heated by Saturn, of course. Just imagine how far away Enceladus is compared to Earth. For those of you who want to do some mathematics, by the way, it takes like 8 minutes to cover the distance between the Sun and the Earth. It's 1 astronomical unit. Let's say we want to send a mission to Enceladus. The radio signal moves with the speed of light. The distance to Saturn is about 9 astronomical units. How long will it take a signal? Will it take us to send a signal to a drone that will be orbiting Enceladus?
Okay, so you said
then a
8
signal
minutes.
to come back. This is an exercise for those of you who want to do some mathematics, right? So while you're thinking about it, we got another question.
Yes,
So
can
what
you
is
can
it?
hear it?
Panspermia theory. Yes, there are some ideas about life that could have arrived on Earth from some other place. We don't know right now. What we do know that we have found some amino acids in space, and amino acids are the building blocks of life. So we don't really know whether some life have arrived on Earth directly, but maybe the building blocks of life, yes. We do know that some living organisms can actually survive in space for quite a long time. Some organisms can withstand a high level of radiation for quite a long time. So maybe some organisms may be hidden inside a meteor and survive, but we don't know yet. The news about phosphine gases in Venus. So why is it important? Venus is a hellish place. It's extremely hot and toxic. In the beginning, Venus was pretty habitable, but that was a while ago. And then Venus had that sad greenhouse gases runaway event. So it was probably the volcanoes on Venus that produced lots and lots of CO2, which we are producing right now by ourselves, which completely changed the Venus and made it extremely hot. So it rains acid on Venus. The air pressure is extremely high. So we didn't expect to find life there on Venus. As you know, most of the missions were toward Mars, toward icy moons, and so on. Not that many people planned the missions to Venus. However, now that we found that phosphine gas, we don't really know what could have produced it. And it may turn out that it is produced by little microbes living in the clouds of Venus. Because we don't know what else could produce this type of gas in a non-biotic way, abiotic way. But we may be wrong.
Sorry, Julia, just a heads up for the time here. I would like to hear you all day, and we have very big questions to answer here, but maybe we can address a couple of more and then hand over to Ulysse in the next 2 minutes. So there is one question from YouTube which reached us, and it's about why is salt an important requirement for life? We saw it in the videos. Why is it an important requirement?
So, a distilled water wouldn't provide you enough nutrients, right? If you think about your cell, the cells that you are made of, your cell is a part of an ocean. The first life started in the ocean, making a little membrane around that little part of the ocean, keeping all that seawater inside with other ingredients, right? So you need salt in order to send signals. You need salt for your cell to work properly. So this is, and I can go more into details, but on a very basic level, that's what it is.
Okay, thank you for this. And the next one and the last question for before we hand over to Ulysse is has to do with how you chose your occupation. So when was the first time you heard about your future occupation? And what's your motivation to study this area?
Science fiction. I really loved reading science fiction as a teenager. So I got my degree, both my bachelor degree and my master degree in astrophysics. And then I went to work at Johnson Space Center. I trained the first 4 expeditions to the International Space Station. So I learned a lot about the human space flight and how the space flight actually affects humans on board the space ship. So, and I always loved education, so I went into astrobiology education later on. I think it's one of the most amazing things that is happening right now. It brings all sciences together. It brings astronomy, physics, biology, chemistry, space law, cognitive science, AI developers, all of them together. So it's quite an interesting field.
It's a very rich discipline, astrobiology. You're right. Just in your talk, you mentioned already chemistry, geophysics, orbital mechanics, and that's just a little part. Thank you, Julia. Thank you very much. We will go on with our next speaker for this session, Ulysse Pedreira-Segade. Ulysse is also joining us from the East Coast, and he's now a postdoc in the Rensselaer Polytechnic Institute in New York. He liked dinosaurs when he was young, but somehow he ended making laboratory measurements with huge machines that can simulate high pressures. So he can tell us about that more. Thank you, Ulysse. The floor is yours.
Thank you, Nasia, and thank you, Julia, for this great introduction. So I'm going to share my screen and hopefully be able to show you my presentation. Okay. Let's see it. Let's go the other way around. Sorry. I want to. Which screen are you seeing right now? Are you seeing the presenter mode or the full screen?
We can see the presenter mode.
Okay. Let's change it around then. Okay. Sorry for this. And here we are. Is that better?
Yes, yes.
Perfect. So thank you very much for letting me talk about my views about what is astrobiology and giving a specific talk about how we can transition from the remote worlds Julia was talking about to the laboratory settings. So we've been seeing in the previous slides that we are extremely interested in those icy worlds because we want to know if life appeared there. We also want to know if it is still there and what does it look like and how can we recognize it. Life in those conditions, living in the oceans of icy worlds where chemistry and physics are similar, but environments might be a bit different and history also is very different, might produce life that is also very different in the end. So the best way probably to go and answer those questions as astrobiologists would be to take the straightforward path and go do direct observations on these remote worlds. And this is what Julia has been talking about. We've been sending missions to several icy worlds. We are sending a new one soon. And this is the video you saw about the Europa Clipper mission that will be launching this decade. And as Julia presented it, whether it is Europa or Enceladus or other icy worlds, what we are really interested in are those hydrothermal vent systems that are at the bottom of the ocean, where the ocean, the rocky cores interact together with heat. They produce those hydrothermal circulation patterns that we see and that we're really interested in. But these ones are pretty remote, and probably the best way to understand them in the first place is to study them directly on Earth. And we actually have the same kind of environments on Earth. They've been discovered in the late 70s, actually, when oceanographers and geologists were studying the seafloor of our planet and suspected that heat was coming out of several places in faults and cracks on the floor. In the late 70s, during a dive with a submarine, scientists discovered these weird structures, these chimneys that were just having a plume of very thick material coming out of it. Since then, we've observed hundreds of them, and they come in different shapes, they come in different colors, they have different minerals composing them, but they're always these kind of chimney structures that are just ejecting some kind of thick material out of them. We call them submarine hydrothermal vents, and we'll talk about them later, but one very striking feature of them is that they are teeming with life. As Julia presented before, on Earth, every time we find these kind of chimneys, we find life everywhere around. And a few meters away from these structures, the ocean floor is actually more like a desert. On these chimneys, you will find things like giant tube worms, snails, crabs, mussels, lobsters, shrimps, and of course, many, many microorganisms that you don't see with your naked eye, but that you can see are around because they will form mats and structures that are generally very colored. We know these environments pretty well right now, and we can place them on a map. And as you see, they are quite common on Earth. They are at the bottom of the oceans, and they are a bit everywhere. We can talk a bit more about this geology if you want at some point. There are, yes, a bit everywhere, but I wanted to talk very quickly about their chemistry and why they're so interesting. These chimneys, these hydrothermal vent systems, they actually originate from the interaction between seawater that is very cold, generally around 2 degrees C at the bottom of the oceans, and a hydrothermal fluid, which is just seawater that was heated up during long interactions with the rock that it went through and seeped through. It was enriched in metals, in hydrogen, and small carbon-bearing molecules. The interactions between the two create a reaction of precipitation of minerals. This is the thick plume that you're seeing there, and also what is building the chimney in the end. This is a place where fluids of very different temperatures collide, and because of that, a very interesting chemistry happens. So the first question I would have for you is, I told you that this is a very hot fluid, the hydrothermal fluid. So why is it not boiling? And that's the question I have for you. So if you want, we can all go to slido.com, and you can get there by typing this event number 7007, and over there your responses will generate a cloud of responses, and we'll see what we have. So let me go there, and I can open the poll for you, and we'll wait a bit to see what kind of responses we have. So why is this hot hydrothermal water not boiling? Too much salt. That's an interesting one. Cool ocean water. Yeah, the mixing of hot and cold. High pressure, pressure. Yes. Any other ideas? The audience on YouTube can also go there, join slido.com. Because of the high pressure, not enough sunlight. Okay. Well, the answer is already in there, and you guessed it, it's pressure and salts. So I'm going to stop that and go back to our slides. This is mainly the reason why. So the high pressure at the bottom of the oceans plus the high salinity of the seawater will raise the boiling temperature of the fluid. And because of that, the way to boil this kind of fluid would be to be higher than 450 degrees C in a general sense. In more details, this is not always true, but in the most general sense. So these environments are actually very interesting to us because they are deep in the ocean, and they are environments of high pressure and high temperature. So what do we know so far? We know that these hydrothermal vent systems are common geological features wherever there is water and rocks interacting with heat, whether it is on our modern Earth or on icy worlds. And they are habitable for life as we know it. We've seen life everywhere when we've seen those chimneys appear. So this gives us another approach to understand if life can just thrive on icy worlds. We can just go directly and study those. This is called the field analog approach, because these environments on Earth are considered to be similar to the ones that might exist at the bottom of the oceans of icy worlds. So instead of sending thousands of robots to other planetary objects, we can actually study analogs here on Earth. And I'm not saying that sending robots is not fun, it's actually super fun. But you can imagine that the preparation of a mission takes a lot of money, a lot of efforts, a lot of time, and a lot of preparation. So we cannot afford to send a lot of them just to test our hypothesis. So direct observations in the field, sampling of material, monitoring of conditions can actually help us understand how particular geology and chemistry of these environments might be favorable for life to thrive. And also, there are actually great places to practice life detection and test instruments for future space mission. This is what's happening right now with the Europa mission. So now that we know that life can thrive on hydrothermal vent systems, and we have a way to understand why that is, the other question is, can it actually appear in those environments now that we know that it's there? So for a chance for it to be in icy worlds, we need to know if it appears there. And this is actually something that was already hypothesized after the discovery of the first hydrothermal systems. In this paper from Corliss, Barros, and Hoffman, there is a citation that I really like, saying that a diverse set of observations suggests that submarine hot springs were the site for the synthesis of compounds leading to the first living organisms on Earth. We hypothesized that a sequence of reactions could occur within or adjacent to these systems. And this hypothesis suggests a number of critical observations to be made, both in the laboratory experiments and on active submarine systems. So since then, we've always hypothesized that hydrothermal vent systems have been essential for the chemistry of life to emerge. And the very interesting part in there, in this citation, is that those scientists call for both an active observation of submarine systems, but also for laboratory experiments, and we'll understand why in a bit. So when we want to look at the emergence of life, we actually introduce a new field of research in astrobiology, which is called prebiotic chemistry. And according to the Encyclopedia of Astrobiology, prebiotic chemistry is the study of the abiotic synthesis of carbon-bearing building blocks, which may have been necessary for the origin of life. Abiotic here refers to all the physical and chemical processes that take place in natural environments that are driven by mechanisms that do not involve any biological activity. So anything abiotic is something that is not produced by life, basically. And so when we study prebiotic chemistry, we study how we can actually create, produce the building blocks of life without the help of life. So really studying the origins of life. And so we'll go back to Slido now, because I have a question for you. What do you think would be a limitation of this approach for prebiotic chemistry, the field analog approach, going straight to hydrothermal vent systems? So let's go back to Slido and let's launch that question. What do you think would be the reason why the field analog approach is not completely suited to understanding prebiotic chemistry? Money and resources, that's a good one. Yes, I like that. So maybe to give you a hint, yeah, time saving, to give you a hint, we want to study, it's too much Earth-like. We want to study something that is not produced by life in an environment that has a lot of life. What can happen there if we want to test hypotheses of reactions that happen without the help of life? I don't see the answer I'm looking for here, but all of those are really great answers anyway. Human interference, yeah. We don't know where to look for. Ooh, there's a lot in there. It is not a good analog. Okay, well, that's definitely very interesting. Let's get back to all of that. So yes, I think all of these responses are really interesting and are actually part of the response. These environments are not perfectly replicating the hydrothermal vent systems on Europa or Enceladus, that's for sure. And it's definitely costly to send submarines all the time when we want to test a hypothesis. So say you wanted to test a hypothesis, you go there and then you realize that, oh, you forgot something. You cannot just take the next boat and go back there and test the next hypothesis. You have to plan for it carefully and it takes time and money. But what I am really interested in is that life is already present in those hydrothermal vent systems. So in a sense, it can contaminate any observations of abiotic reactions because it's there. So it's eating all the nutrients, making most of the reactions that we see. And it's becoming very hard to decipher what is life and what is not because of life in those environments. So the solution for that is to actually transfer what we know from icy worlds or the Earth and put it back in the lab and study laboratory simulations at high pressure and high temperature. So my last question for you would be to understand what that is. This is helping astrobiologists mimic hydrothermal vents in the palm of their hands. But what is it? Do you have any ideas? I'll let you look at this picture, think about your answers, and I'll open the poll. So what was this weird looking thing that I showed you? Gold. It's not gold. Crystal inside a hand warmer, dragon glass. Good one. It's actually not dragon glass in the sense that it's intended. It's close.
The participants are asking you to show the picture again, if you
Oh,
could.
yes, of course.
So the question of the poll is, what is this weird looking thing? And you can answer on the Slido.
Okay. Let's take a look again at your answers. Rock with some crystal salts. So there's a rock, there are crystals, yes. It's not ice. Weird, right? So if I tell you this is something that is really looked for by humans in general, this is a very precious crystal that people really like. Yes, I see it here, diamonds, exactly. So yes, you found it. So this is a diamond found in a rock that's called a kimberlite. We can talk about that later if you want. So why are diamonds helping us mimic hydrothermal vent systems in the palm of our hands? Well, this is because we can build this out of diamonds. This is what is called a diamond anvil cell. And in a sense, it's a small hydrothermal vent system in the laboratory. We have two cut diamonds that are pinching a metal disc. This is weird, right? Like, how can that resemble that? Well, that's because those diamonds are particular. First, they are cut in a very specific way so that they can pinch a sample that is enclosed in a metallic gasket in a small disc. And by applying forces on those diamonds, you actually apply a lot of pressure on that sample. So this is a simulation, computer simulation, that shows you that by applying just a tiny bit of pressure on one of the diamonds, this is like the top diamond here, you can see that most of the pressure is increasing at the tip of that diamond. And this is because pressure is a force that is applied perpendicular to a surface per unit area over which that force is distributed. So pressure is actually a force divided by an area. So for the same force that you apply, the smaller the area, the larger the pressure. So the smaller we make the area at the tip of that diamond, the higher the pressure we can reach. And another thing that is extremely interesting is that those diamonds are very pure, and so they are transparent. And if you were to look from the top of that diamond anvil cell, you would see a ring of metal that is open in the center, and this is where we put our sample. This is the place where we have a chamber for our sample that is enclosed in gold. Gold is used because it's inert. It will not react with our sample in the inside, and you can see the gasket, the metallic gasket around it. So we have a way to apply pressure. We actually can also just heat up the whole device because it's so small, it's really easy to heat it up. And so we can control pressure and temperature of any sample we enclose in there while you looking at it. And this is really interesting because you have a window directly looking at what's happening to your sample. And as the scheme is showing you here, you can use X-ray, lasers, or any other observation techniques to help you identify what's happening to your sample in real time. And this is extremely interesting for us. So like that, we can control the parameters that we want to study without having to dive in the deepest oceans to find those hydrothermal vent systems. Just to show you again, a diamond anvil cell opened this time, this is what it looks like, and you have a ruler to show you how small it is, this is actually 3 parts where you have the top part here, the bottom part here, and this is the way we apply the pressure for this particular system, where there is a membrane where we put compressed gas that will just apply pressure on one side, on the other. And if you look very closely, you can see the diamonds here. This is one of the diamond cut. And on this particular one, the other side is a flat diamond window that we put. So when we prepare an experiment with those, we have to work under a microscope because they are so small. We open the diamond anvil cell under a microscope, we put the metal disc, and we load the metal disc with whatever we want in there, whether it is small organic compounds, whether it is minerals, everything we want to replicate from a hydrothermal vent system, we can replicate it here. And then we just close the system and off we go. We can simulate any of the conditions we want independently or all together, just to have a very simple system we can study in the lab. So for instance, I have been working on a very simplified hydrothermal vent systems in the laboratory, where I was heating up my sample at 200 degrees C, which is a good temperature to mimic those systems. And I was studying different pressures of the seafloor and of the oceanic crust. In my diamond anvil cell in the chamber, I had mineral powders that were common in those kind of systems, along with a solution containing simple building blocks of life. And by just looking at it carefully, I could identify specific reactions happening there. I will leave you on that. And if you have any questions for me, I will be extremely happy to answer them.
Thank you, Liz. Thank you. This was a long trip because we went from the planets and then we arrived at your laboratory. Yeah, so the questions are open. So yes, we have also one school that is following us in live streaming. So there is a whole classroom that is watching the same screen. So this would be great to also get the questions on behalf of the school, and the teacher can do this for their classroom and transfer us the questions in Zoom. I don't know if we have anything from the YouTube for the time being. Not yet, but it's open. The floor is open. I see more participants joined actually for this part. May I ask you something? You mentioned about the little point of your diamond cell, anvil cell. This reminds me of the same principle that we use the injections for, like when you need to take blood, right? Because you don't use a lot of pressure, but because the needle is so thin, you're able to have a lot of power.
That's the same way. A needle can go under your skin very easily because it's so sharp, and actually there's a very little area at the end of it. So the nurse, when a nurse is taking your blood for any kind of testing, they don't need to apply extremely hard forces on you to just go under your skin. This is the same principle exactly.
That's a good demonstration, like we can explain it to classroom. I mean, so we have a question here from Leeds. What is the coolest thing about your job? The coolest. I mean, you have a lot. Just pick the coolest.
The coolest thing about my job, let's see. I would say, so there's a lot of super fun equipment we're working with, like really, really, really fun. I've had the luck to work on a synchrotron one time. So a synchrotron is a giant ring where we produce very intense X-rays, where we can analyze very, very small material. And this was absolutely amazing in terms of technology that was deployed and what we could do with it. But I would say that the best thing is probably working as an astrobiologist with other people in the community, because as Julia was saying it before, and as you were saying it, it's such a diverse community that we got to interact with people that are in our field, but at the same time, not in our field. Like, I cannot say that I am an expert in geophysics or preparation of missions for remote worlds, but talking with them, we can actually understand each other because we have the same goal of finding life elsewhere and understanding how life is in the universe. And this is probably the most satisfying thing when you are in your lab working on a small experiment and you understand that what you're doing is actually helping building robots for remote worlds or understanding philosophical questions about our place in the universe, for instance. Yes.
Great, thank you. One more question. I don't know if we have from YouTube something. Not yet, but maybe I can ask you a question because there is some relation to what your expertise, because there's some relation to your expertise with other things in the society. And we had a question actually here. How long did it take you to reach your current job?
How long from when? After high school?
Let's say from school. Let's say from school.
Okay, so after high school,
Mm-hmm.
so I'm French, so I come from the French education system. After high school, we have 3 years to finish undergrad, 2 years for a master's degree, and then I did my PhD in 4 years. So that's 5 plus 4, that's 9. We arrived there. So 9 years, and now I'm in my 3rd year of a postdoc. So this is a research position of a postdoctorate research position where I'm mostly doing research. Yeah, so it's been quite some time now. It's been more than 10 years for sure. I would say that getting in that current position of working on research journey starts when you finish your master's in France. This is where you have the opportunity to take long internships in research and where you start understanding how things work and how you prepare an hypothesis and start working in a lab and write a scientific publication and communicate about your science. So I would say after 5 years of education after high school.
Okay, and may I use also one fact that it's part of your occupation today, but like exactly today, which I think people will find interesting, that Ulysse is also able to help with analyzing testing that is relating to COVID at the same time. So what
That's
you learned
true.
is not only one thing, is versatile.
That's true. It's always surprising that the skills that you get from studying a very particular thing can be applied to something else. My wet lab chemistry skills, allowed me to be part of that testing facility at my university to help make people safe, I guess.
Yes, and can you explain to the people who haven't heard it before, what is wet lab skills?
So what we call wet lab skills is just being able to work with solutions. So making a solution is just water mixed with different compounds that dissolve in that water. And yes, being able to work cleanly without making spills, working with very small volumes, making sure you don't lose your sample as you go from one tube to the other, and making sure everything stay as clean as possible. So basically you don't put any of your cells or hair or anything in the tube that you're working with.
Great. So I think people are able to relate to what you said, because that's the first access we have to the chemistry lab when we go to school, right? We make solutions. At least I remember this when I was 16. I don't know if it's still the case in all schools, but it must be part of it. And that's how you start. Like, that's wet lab in a way.
Exactly.
The introduction, though. So thank you very much. Thank you very much, Ulysse. I mean, there are more questions. We're open for more questions arriving, but soon we can proceed to the French Q&A. And for that, I will need to call my co-panelist, LeWiBo, who is...
Yes, hello.
Yes, hello. Hi, LeWiBo.
Hi.
So actually...
Good to see you.
Good to hear you. So, LeWiBo, can you tell us a bit about you? And maybe we can, if we don't have any more English questions in English, we will proceed and switch to the French language. And
yes,
let's wait for a few seconds to check the YouTube if there is something. I see nothing for now. And not here. Let me check the Slack, but I think we have it wrapped up for the English session. So thank you very much. to all participants, you're free to stay here, but for the participants who can only understand English, you are free to stay, of course, if you want to understand French by listening, but this will take some time. So thank you very much for attending. We're going to record this part for the French part, and what I was suggesting is to go firstly introduce LeWiBo. So we can switch to French. Alors, non?
Oui,
LeWiBo?
oui, bien sûr.
Alors,
Oui, bien sûr.
tu peux te présenter.
Oui, excusez-moi pour mon vidéo parce que j'ai désolée parce que j'ai avec mon téléphone, mais ouais. Donc, je suis chercheur et je travaille aussi avec Athanasia, Nasia et avec Anastasia et Eugenia avec les projets Lectures Without Borders. Et moi, je travaille dans les recherches interdisciplinaires à UCRI, à Paris, et aussi à Bell Labs en France. Et si vous avez aussi les questions, oui, on peut discuter, on peut.
Peut-être on peut traduire les questions qu'on avait reçues dans
oui,
les chats.
bien sûr.
Non?
Oui,
on peut les traduire.
Je vais regarder, oui. OK. OK. Oui, après un postdoc, quel est votre espoir de trouver du travail? Donc, les traductions, c'est so after the postdoc, what is your how do you expect actually to find the job, right, as a researcher? What is the life of a researcher after postdoc?
On démarre avec une question très compliquée et très sérieuse directement.
Oui, exactement.
Je tiens à dire qu'en France, en ce moment, il y a une loi de la programmation de la recherche qui est en cours de vote et de discussion, et elle va beaucoup changer les choses. La recherche au niveau mondial souffre de plusieurs choses, on va dire. Il y a un problème de financement, tout simplement. On a une explosion des sujets de recherche qui existent depuis un certain temps maintenant. Et on a beaucoup de chercheurs qui veulent travailler, qui sont passionnés par ces choses-là. Et ça a créé, en fait, au fil des années, un espèce de goulot d'étranglement où beaucoup de personnes finissent leur thèse et ensuite attendent pour pouvoir trouver un poste permanent en académique. Trouver un poste en académique, en fait, c'est participer à des concours, généralement de la fonction publique, pour devenir maître de conférence ou professeur des universités plus tard, ou participer au concours pour devenir chercheur au CNRS. Ces postes-là sont rares et il y a beaucoup de compétition dessus. Je crois que, d'après les dernières statistiques, l'âge moyen d'entrée dans ces postes-là, maintenant, il est à 35 ans, alors qu'il était à 25 ans il y a une trentaine d'années, je dirais. Donc, si on parle d'espoir de rentrer dans le milieu, il faut beaucoup de chance. Donc, on essaye et puis on regarde toutes les opportunités qui existent. Et après, oui, c'est malheureusement aujourd'hui beaucoup de chance. C'est pas forcément un message d'espoir que je donne là, mais je pense pas que ce goulot d'étranglement doit empêcher de devenir scientifique et de faire de la recherche derrière. Parce que déjà, obtenir une thèse, en fait, c'est apprendre ce travail de chercheur et apprendre à penser rationnellement, avoir un esprit critique sur tout ce qu'on entend, en fait, et savoir faire un travail de recherche derrière dessus. Donc, que ce soit pour de la science directement, ou pour après un travail plus citoyen aussi, compréhension du monde politique et de quelle est notre place dans cette société. Donc, voilà, pour la longue histoire.
Oui, merci. Merci, Alice. Donc, OK. Donc, il y a aussi des questions comme ça qui... Est-ce que, Ulysse, vous pouvez expliquer comme ça marche en français sur les giant anvil cells.
Bien sûr.
Oui, merci.
Alors,
Peut-être avec une image, c'est possible.
Oui, je vais repartager mon écran.
Ok.
Je vais ressortir l'image pour montrer. Hop. C'est parti. Donc, si on retourne à ça, donc en français, on appelle ça des cellules à enclume de diamant. Donc, on a 2 enclumes faites de diamants qui vont permettre d'appuyer sur un échantillon. L'échantillon est contenu dans un anneau métallique qui est percé en son centre. Et cet anneau métallique, on le perce nous-mêmes, ça prend un certain temps, et on met à l'intérieur un anneau d'or ou de platine généralement, pour être sûr que l'échantillon qui est à l'intérieur ne réagisse pas avec notre échantillon, parce que le métal qu'il y a autour, c'est généralement de l'acier inoxydable, mais quand on le chauffe à certaines températures, qu'on l'appuie dessus à certaines pressions, il a tendance à réagir avec nos échantillons. Surtout que dans l'acier inoxydable, il y a du carbone, et quand on regarde des molécules qui contiennent du carbone, on ne veut pas que ça réagisse avec ce qu'il y a autour. Donc on utilise de l'or, on utilise du platine pour faire ça. Les cellules à enclume de diamant, oui, permettent ça. On appuie dessus et puis on regarde au travers pour voir comment évolue l'échantillon visuellement. On peut voir des cristaux se former, on peut voir des choses précipiter, on peut voir des changements de couleur parfois. Et donc ça nous informe déjà beaucoup. Mais ensuite, on peut utiliser différentes techniques qui vont permettre de déterminer ce qui se passe en termes de chimie à l'intérieur. Et donc, ça, c'est tout un autre volet sur les techniques, mais je peux en parler un peu plus si vous êtes intéressé.
Merci. Donc, il y a aussi OK, oui, il y a seulement des... merci. Et merci beaucoup pour toutes les réponses motivées et pour l'explication.
Avec plaisir.
Oui. Donc, je veux demander à Nasia pour continuer, peut-être. OK, oui. Il y a tous les records avec les sous-titres sont... regarder quelque chose encore une fois, c'est possible aussi.
Je crois qu'on n'a pas beaucoup de questions nouvelles, des questions nouvelles. Pardon pour mon français, je n'ai pas parlé depuis longtemps, alors c'est un peu...
Non, c'est bon.
un peu vieux. Alors, je crois qu'on a répondu à toutes les questions. La question qu'on n'a pas répondu en français, peut-être pourquoi c'est nécessaire de... Non, pourquoi c'est nécessaire? Alors, les wet labs, alors qu'est-ce que c'est? Qu'est-ce que c'est cette set de compétences et comment c'est utile? On peut l'utiliser pour plus d'une chose. Alors, pour l'astrobiologie et pour une autre biologie. Alors, est-ce que tu peux nous expliquer, Ulysse?
Donc, le wet lab en français, ce serait la chimie en fait, c'est les compétences en chimie des solutions aqueuses. C'est savoir travailler avec des solutions aqueuses qui sont de l'eau mélangée à différents composés chimiques. Et en fait, ce travail-là, il démarre, comme disait Nasia tout à l'heure, au lycée avec des tubes à essai qu'on remplit de différents composés. Et en fait, en laboratoire, on travaille généralement avec des très petits volumes parce qu'on économise un peu les molécules qu'on a, les poudres de composés organiques, de sel, etc. On essaye de ne pas trop en préparer pour ne pas avoir à trop jeter derrière. Et donc, on travaille avec des petits volumes qu'il faut manipuler, passer de tube en tube, vérifier que tout est propre en permanence. Et aussi, la plupart du temps, vu qu'on travaille avec des molécules que le vivant aime beaucoup, on essaye de garder tout stérile autant que possible. Donc, on vérifie qu'il n'y a pas de micro-organismes dans les tubes qu'on manipule, et on vérifie qu'on ne va pas contaminer nos tubes avant expérience. Voilà. Et donc, ces compétences-là, en fait, ensuite, servent à beaucoup de choses, puisqu'elles servent dans le milieu médical, par exemple. Donc, on parlait tout à l'heure de tester, de faire des tests PCR pour le Covid. On peut aussi parler de tout simplement tous les tests en laboratoire médical qui demandent les mêmes compétences, ou alors oui, toute la biologie de manière générale qui va utiliser les mêmes choses. Et en fait, on retrouve les mêmes compétences, que ce soit en chimie des solutions aqueuses pour l'astrobiologie ou en biologie de manière générale.
Merci, merci Ulysse. Alors, c'est aussi un message pour les élèves qu'on peut aussi changer de profession en futur parce que cette compétence, ça sert plus d'un.
Tout à fait. Je pense que pour revenir sur l'idée du postdoc et du travail derrière, les compétences qu'on gagne, en fait, peu importe le sujet scientifique qu'on a, en fait, elles sont applicables ailleurs. C'est quelque chose qui parfois est difficile à envisager parce qu'on est tellement généralement passionné par notre petit truc qu'on fait dans notre coin et on se dit, ouais, ça c'est le monde entier pour moi, et en fait, il y a beaucoup de choses derrière sur lesquelles on peut appliquer nos compétences aussi, au final, assez facilement. Ouais.
Merci Ulysse. Et merci LeWiBo pour aider dans cette session française. Alors, toutes les choses seront recordées et seront envoyées à toutes. Alors, à tout à l'heure et à la prochaine.
Merci beaucoup.
Ciao.